Welcome to Test 2 review for trigonometry at Dallas College. This is for Professor Bailey's class, and it's covering Chapters 3 on radian measure and the unit circle, and Chapter 4, graphs of the circular trig function. In section 3.1, we first were introduced to the concept of radian measure and understood the definition here about how 1 radian is defined in relationship to the angle and the arc length of a section and its radius. Okay. Probably one of the important things to remember here is that 1 revolution, which we know as 360 degrees, 1 revolution, which is 360 degrees, is the same measurement in radians as 2 pi. So as we go around the circle 1 time, we've gone around 2 pi radians, or 360 degrees. So since it's 2 pi all the way around, halfway around would be 1 pi. So 90 degrees is pi over 2, half of a pi. Then we hit 180, 270 or 1.5 pi, or 3 halves, or 3 pi over 2, and then again 2 pi. When you're converting these, the first thing I want to tell you is notice this little video camera. These notes are coming from your electronic text in MyLab Math. This is at the end of each chapter. It's called Test Prep. This is Chapter 3, Test Prep. And then each section has a very short video, less than 5 minutes, of an overview of the chapter. So if you go into there, you can actually get a quick overview video, again, less than 5 minutes, of what the key topics were in each section. So I wanted to highlight that. These are, again, right embedded into your e-text. When you open up your text and go to Chapter 3 Test Prep, you'll see each of these videos. So it's another way you can study for the test. When you're doing conversions, I think instead of remembering that multiplying a degree by pi over 180 converts it to radians, I tend to think more in terms of fractions, units, and canceling out. For example, if I want to convert 150 degrees to radians, I have to remember, do I multiply by pi over 180 or do I multiply by 180 over pi? Well, I don't do either of those. What I do is I think of this in terms of what it is and what I want. So I have 150 degrees, so I write that as 150 degrees over 1. Okay, because I know I need to convert this. And what I want is radians at the end, so I know that since I have degrees in the numerator, I need degrees in the denominator to cancel out degrees. And then all I have to do is think about what is the relationship between radians and degrees. Well, I could remember this pi over 180, but for me it's easier to think in terms of 1 revolution. So I think, okay, 1 revolution is 360 degrees, or it's 2 pi radians. And again, I want the radians in the numerator and the degrees in the denominator so that the degree unit cancels out and I'm just left with radians. Notice this is the same thing. If I reduce this fraction, 2 pi over 360, I get pi over 180. But here I just feel like this is kind of information that's stuck in my mind. I know that a revolution is 360 degrees. I know a revolution is 2 pi radians. So it's easy for me to remember this than to say, oh, multiply by pi over 180 or 180 over pi. If I try to remember these formulas, then it's easy for me to pick the wrong ratio, pi over 180 versus 180 over pi. Whereas if I write it out in units, then I know that the unit that I'm given, I need to cancel out, so that other unit, like again degrees in here, I need to get rid of, so I need degrees in the denominator, so I'm going to use this first ratio, this top ratio, instead of the bottom one. Instead of trying to remember, okay, when I go from degrees to radians I do this, and from radians to degrees I do the opposite. Okay. In 3.2, we learned a couple new formulas and vocabulary. The first thing was arc length. Arc length, again, if you look at this little triangular piece, a slice, if you will, think of this as a pizza. The arc length, or the arc, is actually the crust of the pizza, okay? So here we have an arc length that's denoted by the letter S. We have the radius denoted by the letter R. And then we have an angle denoted by the Greek letter theta, okay? Now, all of these formulas that we're using in this chapter require that you use angle measurements in radians. These formulas do not work in degrees. So the first thing is the measurement of the arc length, S, is equal to the radius times theta. This is a formula you need to know. You cannot take notes into the test, so this is something you need to know. The other formula that we have here is the area of the sector, and that's basically how big is your slice of pizza, the whole blue shaded area. And the area of a sector equals 1/2 the radius squared times theta. Again, you need to know both of these formulas, and you need to remember that these formulas only work in radians. In section 3.3, we were introduced to the unit circle. This is a circle who is centered on the origin and whose radius is equal to 1, okay? Now remember, when we first started with all the trig functions, for example, we had sine of an angle was equal to y over r. We built little right triangles by dropping perpendicular bisectors down to the x-axis. But since the radius is now 1, y over r is just equal to y. So one of the interesting things that happened in the unit circle is that we were able to now, with this unit circle, we could relate the value of sine and cosine directly to the x and y coordinate of the unit circle. So for example, the quadrantals, we have 1, 0 at this first point where the angle is 0 or 2 pi or 0 or 360. At 90, the coordinates are 0, 1. At 180 or pi, the coordinate is negative 1, 0. And at 270, the coordinate, the ordered pair of coordinates are 0, negative 1. Now what this means is, because sine is equal to the y value and cosine is equal to the x value because r is equal to 1, this is on the unit circle, then we can see that the cosine of 0 is 1, the sine of 0 is 0. The cosine of 90 is 0, the sine of 90 is 1. I could also say this as the cosine of the cosine of pi over 2 is 0, the sine of pi over 2 is 1. The cosine of pi is negative 1, the sine of pi is 0, and etc. Okay? So this actually helps us kind of figure out some of the values here. Now you have all these values around, and you might again be wondering what's going on here. Remember that we built out what we called our known angles, 30, 45, and 60, by building two different triangles, and then using the relationships of SOHCAHTOA, sine is opposite over hypotenuse, etc. By building those two right triangles, we found that the measures for all the trig functions we could calculate by using those SOHCAHTOA principles of relationships between opposite sides, adjacent sides, and hypotenuse. And so those are the values that you see here in the first quadrant, 30, 45, 60. And then just as we've learned in chapters 1 and 2 about reference angles, that's what's happening in each of these other quadrants. So 150 is the reference angle of 30, 135 is the reference angle of 45, and 120 is the reference angle of 60. Remember, reference angles are measured from the x-axis. So you can see if you look at any of these measures, let's take 30 for example, we get square root of 3 over 2 and 1/2. which is the same numbers here, just different polarity. Same numbers here, reference angle 30, different polarity. Same number here, reference angle, but different polarities. Because, you know, in each of the quadrants, X and Y is different, positive or negative, and so we figure out which value or which polarity to use depending upon which quadrant we're in. Okay? So this is the unit circle. If you know, again, the known measures for the triangles, then you can figure out all of these X and Y values all the way around. And in the last section of chapter 3, we dealt with speed, linear and angular speed. Linear speed is kind of what we know when we're driving our car. This is what we've been dealing with all along. And remember, it's easy to remember the speed formula if you just think of a speed limit sign, 60 miles per hour. Miles per hour is distance over time. Miles is distance, hour is time. So it's the velocity or speed equals distance over time. Now, because we're talking about the unit circle, remember this linear speed. If you think about the unit circle, this would be like a track, and so our linear speed is us running around that track. And so here the distance is actually equal to the arc length, because that's what we're running around. The distance we're running is an arc length. Remember, that's the crust of the pizza. We learned earlier in chapter 3 that arc length is equal to the radius times theta. So we can come up with this alternative formula here. Okay, the middle one on the right. Linear speed equals radius times theta divided by time. On the left, you'll see what we call the angular speed. And so as we are moving around the outside of the circle, if you kind of thought of if you had a string attached to the center of the circle and moved around, notice that that angle is changing as well. And that's all angular speed is. How fast is the angle changing with respect to time? So the angular speed is simply angle measurement divided by time. And because we have this measurement of theta over t, or angle over time, and we see that in the middle formula, we can substitute in this little w guy is actually lowercase omega, Greek letter omega. And so we can also see that linear speed equals the radius times the angular speed. Again, these are formulas you need to know. These problems here that they're given are pretty straightforward, but there were some pretty challenging problems that you really had to be thinking. Okay, if you remember in the lecture, we looked at wrapping a rope around something, and then we also looked at gears interacting and how did the angular change. It's important to think, okay, what is equal there? If you remember the gear problem that we did in the lecture, the arc length was the same, even though one gear was bigger and one gear was smaller. So those are important things for you to be thinking through about what's really going on here and what is equal to each other when I'm solving these. Chapter 4 is all about graphing the circular functions. And the circular functions are just graphing trig functions in connection with the idea of the unit circle, okay? In the idea of the unit circle. So when we think about, again, if we look at, sorry about that. If we look at the unit circle and we think of the sine function first, remember the sine is the y value. So at 0, at x equals 0, the y value, I'm sorry, let me do this again. If we're talking about sine of x, or we're talking about the sine of this angle, this is the angle equals 0, and the y value is the sine value. So we have 0, 0. So we're starting at the origin. What we're doing here is if you think about the angle as being the x value, instead of going around the circle, we've straightened it out. So we go from 0 to 2 pi here, which is 1 revolution, 0 to 2 pi. Okay. As we move up to 90 degrees, or pi over 2, we see that the y value is 1, so the sine value goes up to 1. As we continue moving on to the value of 180 or pi, we can see the y value goes back down to 0, and so that's what's happening here. As we get to 270 or 3 pi over 2, we can see that we're at -1, the y value, and then we go back to 0 at 2 pi or back to 0. Okay, so this is an example of a periodic function, meaning that this function just keeps repeating as we go along, and that it repeats the distance that it goes before it starts repeating is called the period. And then for sine and cosine, the period of both of those are 2 pi, which you might remember makes good sense because we said that an angle on like the circle here has the same trig functions if we go another whole revolution around. And so that's going around another 2 pi and getting back to that same spot. And remember the trig functions, these are called coterminal angles. So we're going all the way around. And at 2 pi we have the period here. We can see that the y values go between 1 and -1 or -1 and 1. That's the range. And trig function, this sine and cosine are continuous, so they cover all values of x. The one thing here to think about too is amplitude. Now amplitude, sometimes people get confused about this because it goes between -1 and 1, so they think the amplitude is from the lowest point to the highest, which would actually be an amplitude of 2. But really what we're trying to see is how far these functions deviate from central. So the way we calculate the amplitude is the distance from the lowest value to the highest value and divide by 2. Okay, so we're really trying to see again, the amplitude is how far it's off center, if you would. Okay, and here we've done the same thing, but with the cosine function, cosine x, and here we're doing the x values. So we start at 1, go to 0, go to -1, 1, go to 0, go to -1, back up to 0, and then back up to 1. Okay, with all very similar properties as well. For tangent and cotangent, we think in terms of that tangent equals sine over cosine. So for tangent, which is here, since tangent equals sine over cosine, wherever cosine is 0, since it's in the denominator, tangent will be undefined, and that's defined by the dashed lines here, which are asymptotes. We can see that at the x values are 0 when we're on the y-axis, either at 90 or 270. But since we don't normally start graphs away from the origin, here we've decided to start at -pi/2, which is the same as 270 from a coterminal standpoint, and pi/2. Okay, and then we can just think about what's happening here at this in this fourth quadrant. Since y is negative and x is positive, and tangent equals y over x, or sine over cosine, negative over positive is going to be negative. So we have negative values hitting 0, and then in quadrant 1 we have both positive x and y, so the tangent is positive. We're going to do a similar thing with cotangent. Cotangent equals the reciprocal of tangent, or cosine over sine. So wherever sine is 0 or y is 0, then the cotangent is undefined, and that of course happens along the x-axis, which is at 0 and pi, which you can see here. And so what happens is the period for tangent and cotangent is pi. It's 1 pi, not 2 pi. And then we have asymptotes at each of those values. Tangent is a increasing function. It goes up from left to right, and cotangent is a decreasing function going down from left to right. Okay. Now all graphs don't look like this. because the expression is different for each potential equation, right? So here we have the standard equation for a circular function or any of the trig functions. So where you see sine, you could put cosine, you could put tangent, cotangent, secant, cosecant. Okay? So there's 4 different variables in here, really 5 if you count x, which is also the angle. But what this is doing, A, B, C, and D, take those shapes that we just saw for sine, cosine, tangent, and cotangent, and manipulate those, and they each manipulate them in a different way. So let's look at what these variables mean from chapter 4. Now, A, B, C, and D do what we call translations of graphs. And so that basic shape that we saw on the previous slide, these will stretch it, they will squish it, they will stretch it and squish it horizontally, they will stretch it and squish it vertically, and then they will move it up vertically or down vertically, or possibly horizontally to the left and the right. Okay? Each of them has a different impact. The variable A is the number in front of the trig function, like 2 sine x, 5 cosine x, 5 secant x, okay? That number, just the number 5 in the example I just gave, is the amplitude or magnifier constant, okay? And what this does is it stretches or shrinks the height of a graph between its max and minimum values, okay? The constant b, and this is b times x, or it's b times a sum or a difference, and it needs to be outside the parentheses. And this was a thing that I emphasized in the lectures, that you really have to be careful about b and d, because the b has to be outside the parentheses if there's a plus or minus d in here, okay? And this is the period constant. This changes the period overall to b of a function. The new period is simply the old period divided by whatever that period constant is. So for example, a sine has a period of 2 pi, so we would have 2 pi divided by whatever the constant b is. Okay, we'll also use this to find the key values, the x values that we're going to graph, and we'll look at that in a minute. The constant out in front or behind, plus or minus this, is actually the vertical shift, and this just moves the graph up or down in the xy plane. And then the last variable, which is probably the most confusing, is d, and this is what's called a phase shift, or simply a horizontal shift, and this moves things to the left and the right. And it's written as a negative because it moves in the opposite direction of what you'd expect. So if d is positive, then we're actually going to move the graph to the negative direction, or to the left. And if d was negative, then we're going to move it to the right. Okay? Now, what we're going to do, it's pretty straightforward, and you need to know this, you need to memorize this or whatnot, is how to find all the translations that happen from a normal or normalized circular function or trig function. Okay, you're going to have values that you already know. This is like for sine x or cosine x, tangent x, etc. You're going to know the x values for that and the y values, which we just saw by looking at the unit circle. For example, the x values for sine go from 0 to pi over 2. These are the angle measures, pi, 3 pi over 2, and back to 2 pi. Okay, the y values are whatever trig function we were doing. If we're doing sine, then it literally is the y of the coordinates, so it would be 0, 1, 0, negative 1, and back to 0. Okay, so you have these in your table. You need to know what those are, and I'm going to point those out in a minute. And then each of the variables, you need to be able to identify them from the standard function, and then simply walk through this table. Now you need to figure out, you need to memorize this table. There's not that much here. You start with the key values. These are your x values. We're going to look at this in a minute. And then you simply divide each of those x values by the period constant, or b. And that gives you a whole new row of x values that you're going to graph. After you do the period shift, you do a horizontal shift, and here you add the d factor. Now be careful, because remember, if this said 2 times x plus 3, d is not plus 3. In order for us to write it as minus, we'd have to write x plus 3 as x minus minus 3. So d is actually negative 3, even if it said x plus 3. It's kind of the opposite. And so we would be subtracting 3 instead of adding it. Okay? The functional values, these are actually the trig values, the sine of 0, the sine of 90, the sine of 180, etc., that are mapped into those x values. All right? So these are our givens, and then we use the variables a and c to shift the amplitude or magnitude, and also the vertical. The way we do that is we take each of the known functional values. Again, for sine it would be 0, 1, 0, negative 1, and multiply that times whatever the amplitude is. And then what this is doing, the amplitude is stretching it taller if it's a number greater than 1, or it's shrinking it if it's a fraction between 0 and 1. After we've figured out the amplitude effect, then we simply add the constant c. Of course, if this was a negative, we'd subtract it. Adding a negative is minus. And this moves the graph up or down very intuitively. The hardest one here is, I think, x, b, and d, making sure, because often you'll see these not written in this kind of parenthesis formula, but you might see 4x minus pi. In that case, you have to factor out the 4. All right? So knowing these kind of steps, how to solve each piece, is really important. And then you can actually graph those x and y values. Wherever you end up, the lowest, the top three rows are x values, the bottom 3 rows are y values, and you're just going to graph the x values from the lowest row that you filled out. For example, you might not have a period shift, but you might have a horizontal shift, or vice versa. So the second row might be blank, and the third row might be filled in, or vice versa. So you're just going to fill out the last row that you fill in from the top 3 rows, and similarly, the last row you fill in from the bottom 3 rows, which gives you your y values. Now, to find those key values, the key points, the x and the y, we're going to use the unit circle. Okay. So again, when we're thinking about the graph, what we're doing is we're stretching out the unit circle. Instead of making it into a circle, we're making it x values. So we go from 0 to pi to 2 pi, etc. Okay. On the unit circle, cosine and sine simply equal the x and y coordinates, since the radius is 1. We already talked about that. And so here we can see the cosine of 0 is 1, the x value. The sine of 0 is 0, the y value. If we go a little bit further to 3 pi over 2, we can see that the cosine of 3 pi over 2 is the x value 0, and the sine of 3 pi over 2 is the y value negative 1. Okay? So what we're going to use for sine and cosine are the quadrantals for the x values. So we're going to use 0, pi over 2, pi, and 3 pi over 2, and then back to 2 pi to do a full period. Okay, those are our x values we're going to use, and then the y values we're going to use are the corresponding y coordinates of each of those points. Since tangent equals sine over cosine, what we're going to do is look for where the cosine is 0, because when a denominator is 0, this function is undefined, and so tangent is undefined. And that actually happens when x is 0. which is anywhere along the y-axis. So we have pi over 2 and 3 pi over 2. Now notice what that means is we'd be starting the graph at pi over 2. And so what we're going to do is use, we are still going to use 3 pi over 2, but we're going to use its coterminal, which is negative pi over 2 and positive pi over 2. All right? And then the last thing we're going to do is for tangent, or excuse me, cotangent, we're going to do the same thing. Since cotangent equals cosine over sine, we're going to find where sine is 0 because that will mean the function is undefined. Okay, and that of course is at 0 and pi. So here's what it looks like for sine and cosine. So the key values we're using for x are the quadrantals 0, 90, 180, 270, and 2 pi. 0, pi over 2, 180, 3 pi over 2, 360, or 2 pi. And the corresponding x values are here. These you need to either know how to figure them out using the unit circle, or you need to have these in your memory, both the key x values and the key y values, which are the functional values, depending upon whether you have sine or cosine. And then you're just going to use, again, the variables a, b, c, and d to convey each row, to change each row. So again here, you would do 0 divided by b, pi over 2 divided by b, pi over b, etc. And then after you did that, for the next row, you would add whatever the value of d is. And again, remember d is the challenging one because it's opposite. So if it's minus 3, then d is positive 3. If it's plus 3, then d equals negative 3. Okay? And then we start all over with the y values here. Again, we have given values by function. Sine is 0, 1, 0, negative 1, 0. And then we take the amplitude, or the a factor, and multiply it times these values. And then after we've done that, we change that row by adding in the constant c, which is the vertical shift factor. Okay, but the starting values are what are important, and you need to know these. You need to know the starting x values, which for sine and cosine are the quadrantals, 0, 90, 180, 270, 360, or 0, pi over 2, pi, 3 pi over 2, and 2 pi. And then, of course, the y values are the x and y coordinates for sine and cosine that you can see here. All right. For tangent, the given x values go from negative pi over 2 to pi over 2, and they also include pi over 4 and negative pi over 4, because these are 45-degree angles, and this is where sine and cosine are equal, which means the tangent value is 1 or negative 1, depending upon the quadrant. And then we have a similar chart for cotangent, and cotangent goes between 0 and pi, and here are the values there. You need to know all the starting values for all of the trig functions, for sine, for cosine, for tangent, and for cotangent. These will not be given to you, and you also need to understand how to either manipulate, how to do, go through this table and manipulate it to get your final graphing. Okay. Finally, the last section we covered was graphing secant and cosecant, and these are actually kind of easy as long as you know how to graph sine or cosine. So when we have a function either cosecant or secant, what we're going to do is we're first going to graph the sine or cosine, whichever is the reciprocal function. So if we have a cosecant bx, we're actually going to graph a sine bx. If we have a secant bx, then we're going to graph y equals a cosine bx. And this is going to be used as a reference. And the way, what I mean there is we're going to use it to figure out what the shape looks like. And so we're going to typically, we're going to graph the sine or cosine with a dashed line. So here you can see the sine of x is a dashed line. Okay, so if I'm trying to graph cosecant, I'm going to graph that same numbers and variables, but use sine and graph the sine function, which we already learned. If I'm doing secant, then I'm going to do cosine. And by the way, there should be an A right here. Okay. The second thing I'm going to do is where I'm going to sketch the vertical asymptotes. And wherever sine or cosine crosses the x-axis, here you can see it at pi and 2 pi for sine, this is a vertical line representing the asymptote or secant, the asymptote of the cosecant or secant. And so we draw those asymptotes in. Again, these happen wherever the sine or cosine is crossing the x-axis, because remember that cosecant equals 1 over sine, and if sine is 0, 1 over 0 is undefined. And so that's the first thing we can do, just knowing those relationships. And then the last thing we're going to do is we're going to sketch the graph of the function that we're looking for, cosecant or secant, by drawing parabolas, which are just U-shaped branches between the asymptotes. Okay? And so what that means is you're simply going to draw a parabola up, meeting at the maximum point, or a parabola down, meeting at the minimum point, and these are going to be between all the asymptotes. So secant and cosecant, as long as you can graph sine and cosine, these are pretty straightforward. And so you're going to graph the sine or cosine, add the asymptotes, and then simply build parabolas that meet up exactly at the point. All right. Finally, remember that there is an extra credit question on this test, and it's from the reading from pages 34 to 68 in Paulo Coelho's The Alchemist, and there are copies at the Brookhaven Library.